More of the square root rules today. We're talking about how you add and subtract square roots, specifically. So how do you add 3 square root of 5 and 4 square root of 5? How does that actually work? Yeah, you know what you do? I think what would be helpful, it's just like adding 3x and 4x. Just treat the roots like they're an x. How would you add 3x and 4x? 7x, huh? Exactly. So how do you think you add 3 root 5 and 4 root 5? 7 root 5, exactly. See how it's the same thing as like x's? It's just like terms, in other words. It's just like roots. What if they give you different roots? Like what if they give you 3 root 5 plus 4 root 11 or whatever? Well, that would be like 3x and 4y. Different roots are like different letters. How do you add different letters? You can't. So you just cannot, huh? They'd be unlike terms, unlike roots. Does that make sense? It's exactly the same rules as it is for letters. Same letters, you can't add them. I'm sorry, that was backwards. Same letters, you can add them, like terms. Different letters, unlike terms, unlike roots, can't add them. So yeah, so that should not be too bad. Let's try number 2. 5 root y plus 9 root y. So number 2. 5 root y plus 9 root y. Can you add those? And so what's the answer going to be on that? 14 root y. 9 and 5 makes 14. 14 root y. We good? So far, anyway? So number 3, 5, third root of 7. Let's try that one. Oops, I already forgot. 5, third root of 7 minus root 2. Plus 3, third root of 7 plus root 2. Is that right? Yeah. Okay. So let's try that one. So basically it's, again, like terms. Any ones that match, you just add those together, combine those, however that is. So 5 third roots of 7 and 3 third roots of 7 makes, 8 third roots of 7. And then what happens with the minus root 2 and the plus root 2? Just cancel out, huh? So there's our answer. So it's just like roots. Making sense? So number 4, 5 root of 12, 2 root of 108. Yeah, good question, Rachel. Yeah, that 3 does. You're exactly right. Whatever number is in the hook, that just stays. Yeah, we don't mess with that at all. Exactly. All right, so how about number 4? Those are different roots, aren't they? We might be tempted to say, well, we just can't add them to different roots, but what's the blanket? You can break them down. Yeah, these can be broken down. So let's first break them down, and then we'll see that they actually become like roots after we break them down. You know what I mean? Like with the trees, the factor trees, like we did last time. So you can use calculators for all this, of course. What times what is 12? Bless you. 4 times 3, and that 4 keeps breaking down. 2 times 2 times 3. So that becomes 5 square root of 2 times 2 times 3. So far, so good. I'm going to send out 2 of those 2's in just a second. Let me go ahead and finish up the other one first. So the 108, I don't know what's all is in there, but I would just start dividing by 2 because I just know it ends with an 8. Just take my calculator out, go 108, divide by 2, and that would be 54. You might recognize that one. If not, just use your calculator. 6 times 9. 2 times 3. 3 times 3. So all these little pieces are the pieces of a 108. So square root of, what's that, 2 2s and 3 3s? So far, so good. I'm going to bring it up here where we have a little more room. So bring it up there. So we have 5 square root of 2 times 2 times 3, and 2 square root of 2 2s and 3 3s. Okay, so what happens from here? Yeah. What's in the hook, by the way? There's nothing in the hook on these numbers, right? The 5, this 5's not in the hook. He's just in the front, right? He's just a big number in the front. He's not in the hook. Same thing with this 2. So what? There's nothing in those hooks. So what does that mean is really in the hook? 2. So that means these are a 2-for-1 deal, right? Remember we talked about whatever number's in the hook, that's the target deal or whatever store you like. That's the deal, right? So it's a 2-for-1 deal. So 2 2s in, sends 1 2 out, and they're gone. So 2 2s in, 1 2 comes out, and when they come out, they multiply. Just like they were multiplying on the inside, they multiply on the outside. When they come out, 2 times 5, 10. What's left on the inside? 3. Good so far. Plus, now what's going to happen with the other one? 2 2s in, 1 2 out, and they're gone, right? And 2 3s comes out, and that multiplies, and they're gone. So what? So on the outside, we're going to multiply 3 times 2 times 2. Any order. So 2 times 2 is 4, times 3 is 12, so that'll be 12. And what's left in the square root?
3.
Yeah, that other 3, huh? And now they are like roots. Is everybody good to there? Everybody see how we got there? I just broke them down, 2-for-1 deal, so 2 2s in, 1 2 out, 2 in, and when they come out, they multiply. And now they are like terms, huh? 10 roots of 3 and 12 roots of 3? 22 roots of 3. They turned out to be like terms in the end. Now, if they'd come out different in the end, I would have just stopped there, right? Like, say this had been a 5 left over or whatever. I would have just stopped right there. I couldn't go any further. But since they're like roots, we can add them. And there's our final answer. Making sense? So just break them down, ship out the 2-for-1 deal, see if they're like roots, if you can add them. No questions? All right, so same kind of thing. So use your calculator, break down those big old numbers. And then these ones have 3s in the hook, so they're going to be a 3-for-1 deal. Got to have 3 matching to send 1 out, don't you? Okay, so 625. So that 5 times 125. 5 times 25. 5 times 5. So that ends up being 5 on the outside, cube root of 4. 5's on the inside. And then the second one, that I don't know about that one, but I know 5 goes in because it ends with a 5, huh? But how many times 5 go in? 20 and 27? 27. 5 is done. Break down the 27. 3 times 9 and 3 times 3. So that's going to be plus cube root of 5, 3, 3, 3. So we good with the breakdown so far? Did you get that okay? So 3 5s inside, sends 1 5 outside, and it multiplies when it comes out, doesn't it? So 5 times 5, 25. What? And they're gone, so what's left inside the root, the third root? That other 5 is left over in there. We good there so far? This making sense? What's happening? And then 3 3s inside sends a 3 to the front of that root, and they're gone. So we get 3 cube root. What's left inside? Again, a 5. So, all right, so now when all is simplified, are they like roots? Yeah, they're both cube roots of 5, aren't they? So we can add them up. 25 of those cube roots of 5 and 3 more of those cube roots of 5 makes 28 of those cube roots of 5. And we're done. Questions? We good? Just big numbers, use your calculator. All right. There's nothing to ship out of this guy. There's nothing to break down. But the 175, you got to break that down. What's in the hook on these guys?
2.
There's nothing, so 2, huh? Yeah. It's 2. So divide by 5. Is it 35? And then break that down. So 5, 7. So 5, 5, 7. So what do we have? Square root of 7a plus 5 square root of 5, 5, 7. And a cubed, remember, is a. All right, so now again, what's in the hook? 2, nothing, so 2. These are square roots, 2 roots, right? So 2 5s in, sends 1 5 out. It's going to multiply. 2 A's, same letters, exactly the same as numbers, right? 2 for 1 deal there also. Out comes an A, and they're gone. So, okay, so what are we left with then? So square root of 7a, that hasn't changed. Out here, 5 times 5?
25.
25, and then the a on the outside, huh? What's left on the inside? 7 and a, huh? Okay, so are these like roots? Yeah, but they are like roots. They're both root 7a. But this one has an a on the outside. So although the roots are like, that's true, the overall outside letters are different, aren't they? The outside letter is different. So we can't just add them. It's not going to be addable. Is that a word? They cannot be added. So what do you do then? GCF. Yeah, you do the GCF. Good. You guys were like in unison there. You take out what's in common. Yeah, what do they both have in common? Root 7a. And root 7a times what? And root 7a times what? You know, what goes here and what goes here? That'll go back to this and this with a plus sign in the middle. Right? Going to be a 1 here. Root 7a times 1 goes back to root 7a. And root 7a times 25a goes back to 25a root 7a. Does that make sense what I did there? I just undistributed. That's what factoring is, huh? It's backwards multiplying. I just said, well, how could I write it so that if you distributed the root 7a to both of them, it would go back? Right? Root 7a times 1 would go back to root 7a. And root 7a times 25a would go back also. And we're done right there. So you do that because, now why did we do that kind of different kind of thing there? It's because these two had different letters outside, didn't they? Meaning that A right there. So they had different letters outside the root, so we couldn't just add them up. We had to do the GCF. Take out what's in common. So we do the GCF when they have different letters outside. Okay, in that last step, is that making sense there? All right. Okay. So how do we, same kind of thing, we want to simplify. This one though, what are we going to do? What do you think we're going to do with 16x minus 80? Factor, yeah, well said. We're going to factor that one. going to factor. So take out a 16, yeah. And then the GCF, right? It's GCF 16 again. So 16 times what? And we're going to have two things in there. 16 times x, and then 16 times what? Just divide by 16 on your calculator. It'll tell you 5. That good? 16 times x, 16x, 16 times 5, 80. Good so far. And then the other one, like that. All right, you guys feeling tricky now? Do you have any thoughts? What can we do at this point? What's that? Yeah, the 16's in a root, huh? What's the root of 16? 4, so that puts a 4 in the front. Does that make sense what we did there? Yeah, the root of 16 is 4. That 4 goes to the front, doesn't it? Good to there. Now, can we add these? Are they like roots? For sure. Do they have different letters in the front? No. What number's in front of this guy? There's an invisible 1. Yeah, 2's in the hook, but 1's in the front. Yeah. So it's 4 roots of x minus 5, and 1 more root of x minus 5. It's 5 roots of x minus 5, and there's our answer.
So only if there's a letter in the front of the root?
Yeah, exactly. Yeah, if there was like an x here or something, then yeah, because you can't add with different letters, huh? Those are unlike terms. Then I would take out the GCF instead. Everybody seeing that difference? So yeah, we didn't have a letter, we just had a 1 there, yeah. So we add them up. Good to there? All right, so so it's all about like terms, isn't it? If the roots match, we add the numbers in the front. Unless they have different letters outside. Then we take out the GCF. Here, let's think about this for a minute. What is going to be, what's the square root of 3 times the square root of 3? Let's think about multiplying the same two things for a minute. If you multiply together, square root of 3 times square root of 3. Yeah, plane 3, huh? Regular 3. Yeah, because 3 times 3 is 9, and the square root of 9 is plane 3, isn't it? Did you track with that, right? So square root of 3, square root of 3, square root of 9, and we know square root of 9 is just a regular 3 with no more root, right? Because that's how you do square roots, right? Whenever you do a square root, you do the square root of the 9, which is plane 3 out of a root. Okay, so we could do a shortcut, couldn't we? We could say whenever you have the same thing multiplied by itself, it's going to end up being one of those regular, not in a root. So in other words, what's the root of 7 times the root of 7 going to end up being? Plane 7. When all is together, it's root 49 and the root of 49 is 7, right? So you can just jump to it's a plane one, isn't it? Or what's root of 11 going to end up being?
11.
Plane 11. Right? What's root of 5 going to end up being? Plane 5. Are you thinking like, Mr. Ham, we've got it. We have got it. Do you really? Because there's something that's fooled people many a time over the years. I'm not wanting to fool them, but I just noticed it did fool them. You ready? You got that down, right? Got that pattern. 2 of the same roots. Oh, and by the way, let me give you another angle just to really strengthen it. Because it's 2 for 1, huh? What's in the hooks here? Nothing, which means 2's. Right? And this is 2 5's in, 1 5 out. Remember 2 for 1 deal? That's another way you could see that it's also true. Right? When you have 2 of the same thing in, that sends 1 of those out, as we've talked about. So, from several viewpoints, you can see that this is a true fact. All right, you ready? You're not going to be fooled, right? You promise me. Square root of 9, square root of 9. A hush falls over the crowd. Is uncertainty setting in? You were so sure. What do you think? So what's the answer?
Nine.
9. Is it 9? But what's the square root of 9?
3 minus 3.
Is it 3?
Well, square root of 9 again.
But wait, but we have two of them.
Right.
So do you keep breaking down?
It's just like 8.
Good question.
81.
Yeah, so what's the final answer to this question?
9.
9? It's not 3?
Because it's
No.
81.
It's 81.
You break it down, it's 99. And then 9 squared is on both sides. So 3 comes out to 9.
Let me try to strengthen your hand in this. So you see the confusion. This is why I give this, we have different answers, huh? So remember, math is pattern. So, because you ever wonder, like, what are we doing here? Am I going to do square root? You're not. Let me be the first to say, in your job, you're never going to do square roots or x fractions or pretty much anything we do in here. You're also not going to probably be asked history questions, like who was the 16th president of the United States. You're not going to be asked, a lot of what you do in school, and there's a question how much of it is totally valuable. Anyway, setting that aside, for math anyway, what we're trying to do is teach you to think logically and patternistically. Better and better. Problem solving, logical thinking, that's what we're doing here. So let me strengthen your mind in the ability to follow patterns closely, precisely, and carefully, because that is a skill that we use in different times. So, here we go. Let me just sometimes verbally helps. Square root of 3, square root of 3. Plain 3. Square root of 7, square root of 7. Plain 7. Square root of 11, square root of 11.
11.
Plain 11. Square root of 5, square root of 5. Plain 5. Square root of 9, square root of 9.
9.
Not 3. Yeah, but the square root of 9 is 3. Yeah, but I'm not the Queen of England either. That has nothing to do. I'm just throwing you up, but I know that enters people's mind and confuses them. We're done square rooting, right? It's out. You can't square root the 9 again. But I know 9 is such a nice number that roots so easily, we're tempted to do it again. But it's out now. There's not a square root there anymore. We can't just root it again because it would be easy. It's done. It's out. Right? It's just not. So nobody will be confused by that now, right? It's out. So remember, 2 in, 1 out. No longer in a square root. Can't root it again. Good? All right. So with that in mind, these questions. Okay. So we're going to take that root 11 that's on the outside. And we're going to multiply to that and then that, huh? Multiply to both those terms. Okay, so what happens as we multiply? Well, basically the rule is the outside stuff has to stay outside and the inside stuff has to stay inside. You tracking with me? So this 4 is an outsider. He's not in a root. So he's going to stay outside and the 11 will stay inside minus. Is that good for the first interaction? The 4 stays on the outside, the 11. They don't interact in any way, do they? They just stay totally separate. And now what happens when the root 11 goes to the 6? Well, the 6 stays outside and the two 11s go together inside. But what do we do with that then? What do those two 11s inside do? 2 in, 1 out. Yeah, so then you take that 11 and go out. So it becomes 4 root 11 minus 6 times normal 11. And they're both gone. A normal 11 comes out, doesn't it? And that's 4 root 11 minus 66, and we're done. How are we doing? Did that make sense there? We doing okay there? Anything I can answer on that? Is that good? And we can't subtract these, can we? We might think we could do something, but these are unlike terms. You know what it's like? It's like having 4x minus 66. One of them's got a root, one of them doesn't. They're just unlike terms. We're just done there.
Take the 4 out.
Yeah, oh yeah, G7, yeah, no, we won't do that. We just did that when it was a root. Yeah, good question, Claudia. We'll just leave it like this. Yeah. It's kind of weird that we do that sometimes. Huh? They just do it when there's a root. I really honestly think it's a weird thing that the author did, but anyway, he just does it when there's a root on this one. Questions on that? Is that good on that? So what happened? Insiders go inside, outsiders stay outside. So the two 11s were in here and they sent an 1 out. That's the only way you can get out of a root, right? 2 in, 1 out kind of thing. Okay, try that one. Same kind of thing. So take that root 5 on the outside and multiply both those terms on the inside. So insiders stay inside, outsiders stay outside. So we'll get minus 2 square root of 5 times 5 plus 8 square root of 5. Is that good so far? And so now what do those 2 5s do on the inside? 2 in, 1 out, huh? So 2 in, out comes a 5. They're gone, and the root's going to vanish, huh? When there's nothing left inside the root, it always just vanishes. So 2 times 5, it's minus 10 there, plus 8 root 5, and we just leave it like that. We don't, they can't add them, huh? They're not like terms. They're unlike roots. So we're done right there. Is that okay? Questions I can answer? Making sense? We can squeeze another one right over here. See number 12. Oh, that's a big one. 3. Yeah, we need third root of 5. Okay, so number here, I'll put it a fresh screen. Number 12. Third root of 5 times third root of 25 minus 6th root. Third root of 200. Okay. So how will that flow? So this will go here, and this will go here. So go ahead and do that, and then just break those numbers all the way down. You know, choose your calculator. You're gonna have some big numbers there, and just break them down. I know what you mean. Your way would do better at that. You're right. So I'm gonna go ahead and just multiply. So this is gonna be, just use your calculator. That would be 125, right? 5 times 25. And this one will be 5. Well, you know what it would be better, actually? Not to multiply, like Claudia was saying. Just leave it 5 times 25, huh? Because you got to break them down anyway. Just leave it 5 times 25 and leave this one 5 times 200. You know what I mean there? That would be a little easier. You know, if you went ahead and multiplied them, that's okay too. I'm just saying this will be a little easier because we have to break them down anyway now to see what can ship out, if anything. Right? So is everybody good so far? That 5, which is an insider, went inside and inside. He didn't touch the 6 on the outside. Okay, let's break them down now. So the 25 is 5 times 5, and I'll bring down that 5. So there's 3 5s there, right? So they're going to ship out a 5. On the other side, I'll bring down that 5. And the 200, what do you do with that? Well, that's 2 times 100. And 100 is 10 times 10. And each of those 10s is 2 times 5. So we got 2, 5, 2, 2, 5, 2, 5. Is that okay? So I broke everything down. Let me rewrite it here. So I have the cube root. That's a 3 in the hook there. 5 times 5 times 5. Minus 6, cube root of 2, 2, 2, 5, 5, 5. Everybody tracking with me? See how I broke everything down there? It's a lot of calculator work, isn't it? And just being really careful with the trees not to drop some of the fruit, so to speak, some of the ends of the vines there. Not to drop anything. So 5, 5, 5 here, 3 2s, 3 5s there. When you break it all down, is everybody good there? So from the beginning, I took this original 5 and I put it in there with the 25, right? And in there with the 200. Then I just broke everything down. Now, you know the deal. It's a 3 for 1 deal. So 3 5s in, because we have 3 in the hook, right? So 3 for 1 deal. 1 5 comes out. They're gone. The whole root vanishes. This is just 5. Minus 6 times, that 6 on the outside sitting there waiting. 3 2s in, ships 1 2 out. 3 5s in, ships 1 5 out. And the root's going to vanish because there's nothing left in the root there. So that's going to become 5 minus, what's that, 60? Which is minus 55.
That, when you, okay, so that 25 you wrote down,
Right?
when it comes out as a 5,
Remember, it's 3. It's 3 5.
yes.
Right, so
it
all
becomes
3
5.
set 1 out.
So don't you have to multiply it, put it in front, how did it cancel out the cube 5 outside?
Well, remember, when everything, the cube just goes with the root. So if the root vanishes, he vanishes. He's just a part of the root.
Yes, but the one outside, doesn't it?
Which one
multiply?
outside?
Outside the parentheses.
So this guy snuck right in there. Insider with insider. He's no longer in the front. And he also snuck inside that one. He showed up right here and right here.
And took the 5.
And took part in the whole shipping out thing. Yeah. Everybody see that? It's a good question. So the one on the outside, right, insiders with insiders, the one on the outside snuck inside both those roots. He's no longer out there. And then I just ship stuff out. That means all of this is a fancy way to say negative 55. How are we doing? Questions I can answer? Feel like you could do this next Monday for the big points? Okay, let's try that one. 4 plus root 7, 4 minus root 7. So remember, outsiders with outsiders, insiders with insiders as you go, right? So we're just foiling that out. Be good here. So this 4 is going to go to both. And so remember, the main rule is outsiders with outsiders. So 4 times 4 is 16 minus 4 root 7. See how the 4 stays outside and the 7 stays inside? He's done. Is that good? So far, he went to both outsiders with outsiders, insiders with insiders, and then this guy goes to both. Minus, a positive times negative is minus root 7, huh? They both stay inside. It's all that good so far. Outsiders with outsiders, insiders with insiders. These cancel, don't they? So we end up having 16 minus. Now, what do these two 7s do? 2 in, 1 out, huh? And the root part vanishes, doesn't it? Because there's nothing left in the root. And then it's just 16 minus 7, which is what, 9? And we're done. That means all that's a fancy way to say 9. Good to there? Questions I can answer?
If the square roots were different, you multiply.
Right. If they were different, I would multiply them. That's right. Okay, want to try that one? Same kind of thing. Those are all insiders, aren't they? All those are inside square roots, so insiders will multiply in. So this A, root A will go to both. So what happens there? It's going to be the root of A times A, or you can make it A squared. Either way is totally fine. Good so far. They both go together under a root. Either AA or A squared. Both are good. Plus root 3A, right? The A and the 3 both go together under the root. He's done. And now this guy will go to both. 10a plus, and now root 10 times root 3, 10 times 3, or you can make it 30. Either way. Good so far. So basically I just put things together so far is all I've done. We good there? Now, two A's inside leads to one A outside, and they're gone. It's just regular A, isn't it? That's the 2 for 1 deal. And what about square root of 3A? There's nothing I can do with it. There's not 2 of anything. Right? Remember, it's a 2. There's nothing in the hook here, which means it's a 2 really, which means these are 2 for 1 deal. There's not 2 of anything, so it just stays root 3A. Same thing with 10A, just stays that way. What about this one? If you break down the 10, it's 2 times 5. There's no pairs there either. There's not 2 of anything. There's a 2, a 5, and a 3. There's not 2 2s. There's not 2 5s. There's not 2 3s. So what do? Just nobody can come out. So what do? Just multiply them together. 2 times 5 is 10 times 3 is 30. And that's it. None of those can combine. They're not like terms, are they? They're all different kinds of roots. This is a plain A, no root at all. This is a root 3A, which is different than a root 10A, which is different than a root 30. We can't add them or subtract them. Now you might think, well, add those, it's 13. No. The parts in the root must be identical. And then when you add, you only add the numbers in the front. Remember the rules we looked at? Like if I had 3 root 7 and 5 root 7, that'd be 8 root 7. See, we only add the front numbers. We never add the numbers in the root. Right? So we're not going to add 3A and 10A. We never do that. Those just tell us they're unlike and may not be added. Make sense on that? Questions I can answer? How many got that? How are we doing there? Okay, about half, huh? Okay, let's try another one. Okay, so what do you do when you have like a 2 on parentheses? Right, 2 of them, huh? Yeah, exactly. So that'll be 6 plus root 7, 6 plus root 7. And, all right. So this 6 will go to both. So 6 times 6, 36, plus 6 root 7. That makes sense. That 6 stays outside the root 7. Because outsiders stay outside, insiders stay inside. Right? So he's done. And then that root 7 goes to both. 6 root 7. Again, that 6 stays outside, doesn't it? Plus, and then these two 7s go together inside. Outsiders stay outside, insiders stay inside. No crossing the line. Okay, and so then what do we have from there? This is 36. See how these guys are like terms? 6 roots of 7 and 6 roots of 7. 12 roots of 7. You just add, right when we have like terms, we just add the numbers in the front. Plus, and then 2 7s in. 1 7 out. And the root vanishes there. And then 36 and 7, they can add because they're just plain old numbers. They make 43 plus 12 root 7. That's our answer. Why can't I add 43 and 12 to get whatever, 55? Yeah, because those are unlike. In other words, it's like 43 plus 12x, isn't it? Those are unlike terms. They just have to stay. Remember, a root is like an x. They just have to stay separate, don't they? They're unlike terms. So we're just done right here. How many got that? How are we doing on that? That's good. Questions I can answer on that? All right. I think I better